Hi, it is JIT UA Courses, and welcome to lesson number 15 of the .NET Developer series, in which we will cover the most relevant topics to becoming a .NET developer. So hit the subscribe button and bell to see new videos on our channel. Okay, let's go. In this lesson, we will learn about multithreaded and asynchronous programming in C#. If this sounds interesting to you, don't hesitate and hit the like button. Multithreaded programming. Process and task. As mentioned earlier, a computer program is not magic. The program code is a certain memory with instructions, and the central processor reads and executes these instructions. In order for memory, resources, network connections, files, etc., as well as the instructions to the processor themselves, not to be mixed up in the operating system in a continuous pile, there is an understanding of the process. A process has just everything it needs to run a program: memory that is allocated specifically for this process, resources that this process uses, and computing power that is allocated specifically for this process. Therefore, our program is basically a certain process for the operating system that starts when the program starts and ends when we close the program. Difference between single-threaded and multi-threaded program. When we talk about the computing power of the process, then such an entity as a thread appears here. A thread is like connecting our program to the processor. It is in the stream that our instructions are calculated by the processor, and lead to a certain result, some action of our program. You may have encountered such a problem that your program froze. You look at it in the system monitor, task manager, and there it says 0% CPU usage, and the program just stopped and does not work. This can happen when, for various reasons, the thread serving the process of your application hangs. And it seems that the program is working, the process has not ended, but the program is not responding, because it is disconnected from the processor because the thread is not doing anything. So in such cases we terminate the program, forcibly in order to restart the process and update the thread, which means the connection to the processor. But the process can have several threads for performing calculations by the processor. They can be executed simultaneously, in parallel, on different processor cores. That's why multi-core processors are made now, which means that more work can be done not sequentially, one instruction after another, but in parallel. For example, a web browser can simultaneously download a file from the internet, and at the same time you can listen to music in one tab and search in another, and the computer can do all this on different cores, and therefore faster and more efficiently. In our process, there can be a main thread that is responsible for the main work of the program, and children worker that can do some auxiliary long-term work. Parallelism and concurrency. Even if our computer has 8 or 16 processor cores, operating system applications and user applications can easily overload them with threads. But even on a single-core processor, we can include several programs and they still work simultaneously. This is because threads can compete with the processor. One stream lasts 10 nanoseconds, then another for 5 nanoseconds, then the first one again for 15 nanoseconds, and so on. Since the execution of thread operations is switched very quickly by the processor, it seems to the user that the programs are executed in parallel, although in fact they work in turn, just very quickly, and we cannot feel it. Thread and thread pool. So, the operating system provides threads for our processes to perform calculations. But the problem is that creating a new thread for a process is a heavy operation for the system. And when we seem to try to make our calculations faster and more efficient and run them in new parallel threads, we can get the opposite result: the program runs slowly and inefficiently. This can happen precisely because we overloaded the system with the creation of new threads. Therefore, for more efficient execution of such parallel calculations, the operating system supports a certain pool of threads, well, like a queue of free threads that do not need to be created, but they are always there. Thus, the process has a certain sequence of tasks to perform certain work. It takes one or more threads from the thread pool to perform these tasks from the queue. When the task is completed, the threads are not terminated but are returned to the pool where they can be reused by other processes. So the system does not need to create new threads, and multi-threaded calculations are much more efficient. Thread. A thread is the basic unit of execution in a process and is responsible for executing the program logic. By default, each application or program will have one thread to execute the application logic, and this thread is called the main thread. So we can say that every program is single-threaded model by default. For example, in the Windows operating system, if we open Microsoft Excel and Word at the same time, each process of the program will run in separate threads. We need to import the system threading namespace into our threading application. After importing the system threading namespace, we can create or access threads using the thread class. Generally, when we start the program execution, the main thread is automatically created to handle the program logic. If we create any other threads in our application using the thread class, they will become child threads to the main thread. Thread info. If we want to access the main thread that is executing the current program code, we can access it using the current thread property of the thread class. Below is an example of getting details of the main thread using the current thread property of the thread class. When we run this program, we should get the output below. The main thread is responsible for executing programming logic in a synchronous manner, i.e. one after the other. If we want to run multiple tasks at the same time, we need to create child threads in our application. We can create a thread by extending the thread class. To create a new thread, we need to pass the threadStart delegate as a parameter to the thread constructor as shown below. Here, the threadStart parameter is the method executed by the new thread. After creating a thread, we need to call the start method of the thread class to start the execution of the newly created thread. Thread overview. Below are important points you need to remember about threads. A thread is the basic unit of execution in a process and is responsible for executing the program logic. By default, each application will execute a single thread to execute the application logic, and this thread is called the main thread. To work with threads, we need to import the system threading namespace into our application. After importing the system threading namespace into our application, we can create or access threads using the thread class. The main thread will be created automatically to handle the application logic. If we create any other threads in our application using the thread class, they will become child threads to the main thread. Synchronization blocks. The lock block is useful for obtaining a lock on a specified block of code to ensure that only one thread can execute it at a time. If any other thread wants to execute the same piece of code, it must wait for the thread holding the lock to complete its execution. Generally, the lock is useful when working with multi-threaded programs to ensure that a single thread can access a specific piece of code. Lock syntax. Below is the syntax for using the lock to obtain a lock, synchronization, for a specified piece of code. Here X is the key of the synchronization block, and in the lock statement, we need to write the code that we want to allow access for one thread at a time. Below is an example of using the lock to wrap a specific piece of code to allow one thread to execute at a time. We created several threads, T1 and T2, and started executing the printinfo method at the same time. Here, in the printinfo method, we have used the blocking operator to obtain a mutual exclusion of blocking for the execution of the for loop code to allow only one thread to execute at a time. When we execute the above output, we will get the output as shown below. If you observe the result, even if we run multiple threads simultaneously to execute the same function, the blocking statement makes the second thread wait until the first thread finishes its execution. In the above example, if we did not use a blocking instruction, then multiple threads would be executing at the same time. Several threads started executing the printinfo method at the same time. Here's how we can use the lock statement to synchronize access to a specified block of code to ensure that only one thread can execute it at each point in time based on our requirements. Asynchronous programming. The task is useful for asynchronously performing operations on threads from the thread pool, and it was introduced in the .NET Framework 4.0. To work with task objects, we need to import the system, threading, tasks namespace into our application. Once we import the system, threading, tasks namespace, we can create or access task objects using the task class. Typically, a task class will represent a single operation that will be executed asynchronously on a thread from the thread pool, rather than synchronously on the main application thread. We can create a task object using the task class. The following is an example of creating a task object using the task class and starting it by calling the start method of the task class. In the above code snippet, we create a task object, T1, and start it using the start method. Instead, we can also create a task object that will run automatically using the factory property or the run method as shown below. So we can create task objects in different ways according to our requirements. From a performance perspective, the task, run or task factory.startNew methods are better for creating and scheduling compute tasks. If you want to separate task creation and scheduling, it's a good idea to create the task separately using the task class and call the task, start method to schedule the task to run at a later time. Waiting for task completion. As discussed, tasks will be executed asynchronously in a thread pool thread. The thread will start executing the task asynchronously with the main application thread as soon as the task is created. A child thread can continue its execution until it completes its task even after the parent thread has finished executing. If we want to force the execution of the main thread to wait until other tasks have finished executing, we can achieve this using the task, wait method. The wait method will block other executions until the assigned task completes its execution. The following is an example of using the wait method to force program execution to wait unconditionally until a task completes its execution. Overview of tasks. Below are important points you need to remember about tasks. A task is useful for asynchronously performing operations on threads in a thread pool. To work with task objects, we need to import the system, threading, tasks namespace into our application. We can create or access task objects using the task class. The task class will represent a single operation that will be executed asynchronously on a thread from the thread pool, rather than synchronously on the main application thread. Often, the program performs such operations that can take a long time, for example, accessing network resources, reading and writing files, accessing the database, etc. Such operations can seriously load the program. This is especially true in graphical, desktop or mobile applications, where long operations can block the user interface and negatively affect the user's desire to work with the program, or in web applications that must be ready to serve thousands of requests per second. In a synchronous application, when performing long-running operations on the main thread, that thread would simply block for the duration of the operation. And so that long operations do not block the main operation of the program, you can use asynchrony. Asynchrony allows you to transfer individual tasks from the main thread to special asynchronous methods and at the same time use threads more economically. Asynchronous methods are executed in separate threads. However, when a long-running operation is performed, the asynchronous method thread will return to the thread pool and be used for other tasks. When the long-running operation completes its execution, a thread is allocated again from the thread pool for the asynchronous method, and the asynchronous method continues its work. Two statements are key to working with asynchronous calls, async and await, the purpose of which is to simplify the writing of asynchronous code. They are used to create an asynchronous method. The asynchronous method has the following characteristics. The method header uses the async modifier. The method contains one or more await expressions. One of the following is used as the return type. Void. Task. Task t. Value task t. An asynchronous method, like a regular method, can take any number of parameters or none at all. However, an asynchronous method cannot define parameters with the out, ref, and in modifiers. It's also worth noting that the word async in a method definition does not automatically make the method asynchronous. It only indicates that this method can contain one or more await expressions. The print asynchronous method is defined here. It is asynchronous because it has the async modifier in the definition before the return type, its return type is task, and the await expression is defined in the method body. It is worth noting that the print async method does not explicitly return any task object, so it is almost the same as void, but since the await expression is used in the body of the method, the task type can be used as the return type. According to convention, it is nice to use the suffix async, print async in the name of asynchronous methods, although it is not necessary to do so. Error handling in asynchronous tasks. Error handling in asynchronous methods using the async and await keywords has its characteristics. To handle errors, the await expression is contained in the try block. In this case, the print asynchronous method throws an argument exception if a string of less than 3 characters is passed to the method. To handle the exception in the main method, the await expression is placed in the try block. As a result, an exception will be generated when await print async with hi as an argument is called. However, the program will not crash its work but will process the exception and continue further calculations. It should be taken into account that if the asynchronous method has the void type, then in this case the exception is not transferred to the upper context. Accordingly, we will not be able to process the exception when the method is called. In this case, even though the asynchronous methods are called in the try block, the exception will not be caught and handled. This is one of the disadvantages of using asynchronous void methods. This is all for this lesson. Thanks for watching. Hope you enjoyed it. Don't forget to subscribe to the channel and hit the bell so as not to miss the following videos in the series. Feel free to leave a comment and like this video. You are also welcome to leave any questions in the comments section. I will be happy to answer them. And also I encourage you to help brave people in Ukraine to defend themselves in this horrible war. Please use the QR code or links in the description to visit charitable foundations that help Ukraine. Thanks. See you in the next videos.